Hello everyone, welcome back to another video. Today we're going to be looking at physical science paper 1. That is the May and June question paper 2022. Alright, so we are going to go back again to circuit theorems. That includes your Ohm's law, EMFs and everything, and that all resides in question number 8. Alright, so question number 8 reads as follows. We're given a diagram, a circuit diagram. Now they are saying that in the circuit below there is a battery. There is the battery. They are saying it has an unknown EMF. There is EMF, and then it also has an internal resistance of 0.5 ohms, which is connected to two resistors of 4 ohm and 8 ohms each. So these are the two resistors. They are saying this battery, which they are referring to in the first line of the statement, this battery is connected to these two resistors. And they are also mentioning that there's an unknown resistor which is connected also in this circuit. There we see the resistor R. Alright, there's two major words in here. That is the EMF and that is the internal resistance. Okay, for EMF and internal resistance, please refer to the previous videos. I'm going to attach the description in the link in the description below. Okay, cool. They are also saying that we must ignore the resistance of the connecting wires. Cool. I went deep into why we should always understand what the statement means when they are saying we must ignore the resistance of the wires. You will also find that in the previous video. Okay, let's go to the first question, which is question number 8.1. 8.1 reads as follows. The three external resistors are ohmic conductors. Okay, where are the resistors? They are saying external resistors. External to what? There is a power source in here, and they were saying the power source is connected to resistors. So when we talk of external, we refer to anything outside of the battery, not the internal resistance, because you can't physically see the internal resistance. Okay, they're saying there's these three resistors here, and they are mentioning that these are ohmic conductors, and we're asked to define what are ohmic conductors. Okay, ohmic conductors. There's two words in here. There is a conductor, and then there is ohmic. When we say something is a conductor, it purely means that it does conduct current, or it allows the flow of charges through it. That is a conductor. An insulator, which is the opposite of a conductor, insulates or resists the flow or doesn't allow the flow of charges through it. Okay, so we now know what a conductor is and know what an insulator is. Now in this question, they are further describing this conductor as ohmic. Okay, ohmic conductor. Okay, when we say something is ohmic, let's just maybe try and run away for 1 second. When we say someone is a South African, we know that that person belongs or was born in South Africa or is a resident in South Africa. When we say something is blue, this is a blue shirt, we know that it is a shirt, but then specifically it is blue. But then now, when we talk of ohmic, it means that this needs to be related to Ohm's law. It is ohmic, all right. But what does that mean now? Because we're referring to a conductor. If we tie in these two words, it means that this is a conductor that obeys. Remember, I said someone is a South African. It means they reside in South Africa. They obey the laws of South Africa. If it is an ohmic conductor, it means it obeys. This type of conductor obeys the laws of Ohm's law. So a conductor, an ohmic conductor is simply a conductor. This is a conductor that obeys Ohm's law. That is, Because you ask yourself, what do I mean by that? It obeys Ohm's law. What is Ohm's law? Ohm's law means that, or when you say it obeys Ohm's law, it means that the potential difference across this conductor, ohmic conductor, if this is the conductor, the potential difference means there's a voltage here, there's a voltage here, there's a voltage drop here across this resistor, and we call that a potential difference because there's a potential here which is V2, then there's a potential here which is V1. So potential difference is the change in voltage. The potential difference across this conductor the potential difference across this conductor is directly proportional to the current through the conductor. That is what Ohm's law says. So this type of conductor obeys Ohm's law, meaning that the potential difference, you can always know that potential difference across that conductor will be directly proportional to the current through it. It is directly proportional to the current. Alright. That is what we call an ohmic conductor. Alright. Let's move on to the next question, which is 8.2. Alright. Question 8.2, we're given a statement there that says that switch S remains open. Now, where is switch S? There is switch S. They are saying it remains open, and that the voltage or the voltmeter V1 reads 3.2 volts. Okay. Now they're asking us on 8.2.1 to calculate the current through the battery. Okay, let's try and understand this statement. So 8.2.1, they are saying that this switch is open. Now understand me. When a switch is open, remember we say something is a conductor. When you remove the conductor, it means that there will no longer be flow of current on that path. So if we're saying here this switch is open, it means that we can totally ignore this side of the circuit, because if current moves out of the battery and comes here, it can't come this side because there is no conductor. Alright, so we can redraw this statement or redraw this diagram as 4 ohm, 8 ohm, there is the battery. Alright. Okay. Then they are saying that this voltmeter here measures 3.2 volts. Then that is your V2. Okay. That is our new circuit. It has the internal resistor there, 0.5 ohm. This whole thing here is your EMF. They are saying that the potential difference across 4 ohm is 3.2. Remember on the previous question we said if you measure the voltage here and you find the difference in potential, that will tell you about the potential difference, which is what a voltmeter measures. So across this resistor, there is a potential difference of 3.2 volts. Now, the question is asking us to calculate the current through the battery. Okay, let's try and follow the current through the battery. This is the battery, and current moves in this direction. Oh, so we see the current goes through that resistor, then continues and goes through this resistor, then comes back to the battery. You ask yourself, did that current change or did it split into two, whereby it goes into one path and then the other path? here we see that the current is continuously on the same path. It doesn't split into two, which means this circuit is a series connection. Okay, now you should be asking yourself, but when we got to this point, why didn't the current go to the voltmeter and the other one goes to the 4 ohm? Please check out our previous video where we stated that no current goes to the voltmeter. Okay, now they're asking us, so which means that the current through the battery or coming out of the battery is the same current that goes through this resistor and this resistor. Okay, what do we have in here? Do we know anything about the current that passes through here? We are given that the potential difference across this resistor is delta V is 3.2 volts. And we just mentioned that that resistor obeys Ohm's law. Right, what does Ohm's law say? Ohm's law says that voltage potential difference is equal to current multiplied by resistance. That is Ohm's law. You can also write it as follows: the current through that resistor is equal to the voltage across the resistor divided by the resistance. Right, what do we have in that circuit? We know the potential difference across that resistor, which is our voltage here, and we know the resistance of the resistor, and that resistance is 4 ohms. So this is going to be 3.2 volts over 4, which is going to be, punch that on your calculator, 0.8 volts. Oh no, 0.8 amps, because we're calculating the current. All right, that is 8.2.1. Let's go to 8.2.2. Right. Now, in 8.2.2, they're asking us to calculate the EMF of the battery. Remember, we went deep into what an EMF is. We said, just to give you a glimpse, when you buy a battery from a shop, they tell you that it's a battery that is capable to give you 24 volts. That is what we refer to as the EMF. That is the voltage that will never change, which describes the battery. But that doesn't mean that over a span of time, when you connect that that battery on your circuit, you'll always get that voltage out. What can cause it to decrease is when you have an internal resistor. Okay, now how do we go about calculating that original EMF of the battery? It means now we need to consider that the internal resistor of the battery has eaten up some of the voltage, so much so that we're no longer giving out that initial 24 volts we thought we're giving. So to understand the initial EMF, or the certified voltage of the battery, we need to take into account to what voltage is given to the circuit, adding the voltage that is being charged or taken by the internal resistor. In a simple equation, we say that the EMF is going to be the sum of the voltage that is dropped on the external resistors, that is going to be the current through the external resistor times the external resistor. And then we add the voltage that is being charged or taken by the internal resistor. That is going to be I multiplied by R internal. All right. Now, one question you might have is, what is that I that I'm talking about? I is the current through the battery or coming out of the battery. All right. And remember, on the previous question, we just calculated that current. So we know the value of this current. Do we know the value of the internal resistance? Yes, that is given. That is 0.5 ohm. We know that. Do we know the external resistor? Remember, I explained at the start of this question that external resistance means outside of the battery. And what is outside of the battery there is those two resistors which are in series. All right. So R external, we can calculate R external as the addition of those two, which is going to be 4.8 ohm, 4 plus 8 ohm, which is going to be 12 ohm. All right. Therefore, our EMF, we substitute everything, is going to be 0.8 times 12 ohm, which is what we're substituting from here. Then you add 0.8 multiplied by 0.5 ohms. This will give you your EMF. And that is equal to 10 volts. All right, 10 volts. That will never change. So we can even come to our diagram here and write it as 10 volts. That is the value of the EMF that, let's say, you get when you buy the battery, or what you're promised that this battery is capable of giving out. So that will never change. Right, now we can move over to the next questions. Okay, question number 8.3.1 says that switch S is now closed. Let's come back. Now we are closing this switch. It means it's no longer insulated. It is no longer open. Therefore, there is a conductor here, which then means that current will now be interested to flow through this resistor as well as this connection. All right. So if we close that resistor, that thing there, it is closed. So your current part now will move out of the battery, come and split here into two. All right. Now they're asking us to calculate the resistance of resistor R. They also mentioned that the voltmeter V2 reads 8.8 volts. Now let's try and explain what does V2 mean. I mentioned to you that you buy this battery, they tell you that it is capable of 10 volts, which is the EMF. All right. Over time, it builds up an internal resistance. When you hook it up on a circuit and you're measuring the potential difference across the battery, which in actual sense, it should be 10 volts. It shouldn't just change. But now that you are measuring it, having the internal resistor, it means it has dropped now. And that is what V2 is measured. That is the voltage that goes to your external circuit. Okay, so if we come back to that initial equation, which is, this is 8.3.1, EMF is equal to I times R external plus I times R internal. Let's analyze that equation. There is I times R external and I times R internal. The external resistor and that current denotes the actual voltage that goes to your external resistors. And that is exactly what V2 is measuring. And they're telling us that V2, which we can write this as V2, it is equal to 8.8 volts. Now the question is saying we must figure out what is the resistance of R. Okay, now how can we go about that? So this is the first explanation of exactly what does V2 refer to. So we can rewrite this as the EMF, we have the initial equation, EMF is equal to 8.8 volts plus I times R internal. It's going to be 0.5 multiplied by I. Now you ask yourself, what is different from this I here and the one that we calculated previously? Right, so the previous I only considered this circuit in here. So there was the external resistor, which was 4 plus 8. Now it is no longer 4 plus 8. I here, which we are referring to here, I that comes out of the battery, comes here and splits into this path and this path. The most important part is that this voltage that we're measuring here is the voltage across this parallel circuit. We say that this is the voltage that goes to your external circuit, which means if we measure here, we should have a potential difference of 8.8. Let me try and denote it. Should have 8.8 here, 8.8 volts. And also across this resistor here, we should also have 8.8 volts because the voltage across a parallel circuit is constant. But what changes? It is the current. So the current comes here and splits into this part and splits into this part. So if we refer to this one as I1 and I2 this side, these currents add up and come back to your initial I here, which we are referring to in this case. But we don't know what is the value of this resistor. Okay, do we know what the value of this current is? No. Do we know what this one is? We can find it out because we have the potential difference across this path. Alright. But do we know the current that comes out of the battery? Do we know the current that comes out of the battery? There, we can solve for that current because we know the EMF, which will never change. The EMF is equal to 10 volts, calculated from the previous question. Alright, so if we solve for this, it's going to be 0.5 I, then we take this 8.8 to this side, it's going to be 10 volts minus 8.8 volts, which this is going to be 1.2 volts. Alright, then you can find I by saying 1.2 divided by 0.5. This is going to be 2.4 amps. Oh, okay. So we know that the current that comes out of the battery is 2.4 amps, which means that I1 plus I2, I, which is 2.4 amps, is equal to I1 plus I2. These are all should be giving us 2.4 amps. Right. We know I, it is 2.4 amps. I1 is the voltage across this part divided by this total resistance in here. Alright, so it's going to be a voltage reading of V2 divided by 4 plus 8. What about I2? I2 is still the voltage here because we said the voltage across the parallel circuit is the same. So we have V2 divided by R that we don't know. This is all equal to 2.4. Alright, so we can substitute here by our V2, which is 8.8 volts. 8.8 volts over 12 plus 8.8 volts over R that we don't know. This should all give you 2.4 ohms. Right, then you can solve for this. If you take this to the other side, it's going to be 2.4 minus 8.8 over 12. That is going to be 8.8 over R equals to 2. So it's going to be, if you subtract this from this side, it's going to be 1.67. Therefore, when you solve for your R in here, you can go back to your maths. You're just going to have 8.8 divided by 1.67. That is 5.28. So R is going to be 5.28 ohm resistor. So you just find a reciprocal in here or do cross multiplication to solve for R. Alright, so we found the value of R to be 5.28. That is the value of our R. Alright, so let's move on to the last question. Okay. Alright, so the last question is asking us, they are saying that the battery becomes heated when voltmeter V2 is replaced by a connecting wire. Explain why this is happening. Okay. Let's first draw the new circuit in here. They are saying V2 is replaced by a wire, and they are saying the battery is heating up. So if you have the battery, right, internal resistor, Then there is your V. It's just a connecting wire there. Then you have the external resistor, which is going to be those two resistors here, and then that big one this side. Okay, then you have your voltmeter there. Okay, they are saying that this battery is heating up when you remove the voltmeter and put in a wire there. When you just have a bare wire, they are saying that in the initial statement, remember that you must ignore the resistance of the wires. When you ignore something, it means that it has no resistance at all. Meaning that if you were to say there is a resistor here, you'll call it it's not ohm resistor. Okay, now let's try and break this question apart. They're saying it's heating up. What does heat mean? Heat means that there is energy, because you cannot just talk about heat from water. We're talking about that if you touch the battery, you'll burn. It means there's energy related to this. And then what is energy? Energy is the ability to do work. Energy is the ability to do work. What is work? Work is power. Right. Let's break this apart again. We said the battery is heating up. And when it is heating up, it means that we can actually feel the energy that is dissipated or that comes out of the battery. But energy, we always link it to the ability to do work. And in physical terms, when we talk of work, we refer to power. All right, which means here we need to calculate the power that is actually dissipated by the battery. How do you calculate power of the battery? Power is simple. The formula, power is equal to voltage multiplied by current. All right, there's voltage and then there's current. This is the voltage from the battery, and then this is the current that passes through the battery. Do we know the V of the battery? Yes. That refers to the potential difference across the battery, or rather your EMF in some cases. But do we know what is the current through the battery in this new circuit? Now let's say I'm a current. If I am current, I'm going to come out of the battery this side. Then I see lots of resistors this side. I have a choice of coming here, but I also see a wire here which has 0 ohm resistance. There is some resistance here which is from a parallel connection. There is no resistor. All of that current will go this side, because we say current is inversely proportional to resistance. That is your Ohm's law. Ohm's law is I equals to V over R. Current is inversely proportional to resistance. When the resistance is too big, it's too big, there will be no current going that side, which is what we're seeing, that when there was still the voltmeter here, the current could come out of the battery, but it never went to this side because the voltmeter has high resistance. But now that we see there is no resistance at all of that current goes there. So how do we calculate that current? We come back here. We say the current is V over what is the ohms there is 0. Or it is an extremely low value, 0.000001. That is a very low resistance or negligible resistance. If you type any number here, you put maybe 2 divided by a very small number, you'll see that that current that goes here is infinity. It's too big. The current is too big. Current is too big that flows in that side. If we come back to power here, because that's the current we're referring to, that current has to come from somewhere, of which it comes from the battery. So if you take the voltage from the battery, you multiply it by a very big current. That is going to give you a very big power. Very big watts, that is infinity watts. Alright. If this is infinity watts, Remember, from the start of this question, we mentioned that we're trying to find or make sense of why there's too much energy coming out of the battery, or the heat coming out of the battery. Then how do we calculate energy from here? Energy over time is equal to power divided by time. And we just calculated that power is infinity, therefore this whole thing is infinity joules. That is why the battery is heating up. So first point, there's too much current because there's a short. So we call it, when there is just one wire connecting, it's a short circuit in the circuit theory. It's a short circuit, meaning there's very low resistance. If there is low resistance, more current is going to go there, or call it infinite amount of current is going to go through that path. When there's too much current going through a specific path, the power increases, because power is equal to V times I. Right? When the power increases, energy increases, because energy is equal to power divided by time. Energy is directly proportional to the power dissipated. That is why we're finding this observation that the battery is giving out too much heat. Alright, if you found this video useful, please give the thumbs up. Also give us a subscribe, and if you have any questions, please leave them in the comment section below. Alright, thank you guys.